Hello dear students. Today we will discuss on IR spectroscopy. First of all, we should know what do we observe in UV spectroscopy. In UV spectroscopy, we have seen that the molecules are irradiated with electromagnetic radiation with particular frequency, and it involves the promotion of electrons sigma, pi, or n star electrons from lower energy ground state orbital to higher energy molecular orbital, and fixed quantity of energy is required for electronic transition. Hence, electromagnetic radiation with particular value of frequency will able to cause excitation above or below which will not be absorbed by the molecules. What electronic transitions in UV spectroscopy occurs? There are four types of electronic transitions: sigma to sigma star, pi to pi star, n to sigma star, and n to pi star. Electronic transitions occurs where sigma to sigma star occurs for alkane molecules, and pi to pi star transitions responded by the molecules of alkenes, carbonyl compounds, alkynes, azo compounds, and n to sigma star transitions responded by the molecules having oxygen atoms, nitrogen, sulfur, and halogen compounds. And N to pi star transition occurs for carbonyl compounds. Now, the effect of electromagnetic radiation on the molecules. These are the various effects, molecular effects, and these are the lower frequency and higher wavelength to higher frequency shorter wavelength range. And in this region, various molecular effects occurs. Here ionization, electronic transition, molecular vibration, rotational motion, and nuclear spin transitions. Today, we will discuss on IR spectroscopy. So before going that, we will go to the history of the IR spectroscopy technique. Infrared radiation was discovered by William Herschel. We know he was an astronomer, composer, and brother of fellow astronomer Caroline Herschel, with whom he worked. Herschel constructed his first large telescope in 1774, after which he spent 9 years carrying out sky surveys to investigate double stars. And he was the pioneer of the use of astronomical spectrophotometry using prism and temperature measuring equipment to measure the wavelength distribution of stellar spectra. In the course of these investigations, Herschel discovered infrared radiation. Herschel was carrying out his investigation on energy levels associated with the wavelengths of light in the visible spectrum. During his investigation, he was observing one well-known visible spectrum of rainbow colors. For that purpose, sunlight was directed through a prism. He was interested for searching relationship of visible spectrum from blue to red with the analogous wavelength or frequencies. It is well known fact that spectroscopy is the study of interaction of electromagnetic waves with matter. The wavelengths of the colors is directly related to the energy levels of the rainbow colors. Herschel, by slowly moving the thermometer through the visible spectrum from the blue color to the red color and measuring the temperatures through the spectrum, he observed the increase in temperature from blue to red part of the spectrum. Then Herschel took decision to measure the temperature just below the red portion, thinking that the increase of temperature would stop outside the visible spectrum. But to his surprise, he found that the temperature was even higher. He called these rays, which were below the red rays, non-caloric rays or invisible rays, which were called later infrared rays or IR light. This light is not visible to human eye. A typical human eye will respond to wavelengths from 390 to 750 nanometer. The IR spectrum starts at 0.75 nanometer, where 1 nanometer is equivalent to 10 to the power minus 9 meter. The infrared spectrum is divided into main infrared, near infrared, and far infrared. Now, the infrared regions. Main infrared regions belongs to zero point 0.8 to 2.5 micron. That is 12,500 to 400 centimeter inverse. Near infrared regions belong to 4,000 to 667 centimeter inverse, where far infrared region belong to 15 to 200 millimicron, that is 667 to 100 centimeter inverse. The first region, that is main infrared region, allow the study of overtones and harmonic or combination vibrations. The near infrared regions is to study the fundamental vibration and rotation vibration structure of a small molecule, whereas the far infrared region is for the low heavy atom vibration, metal ligand, or the lattice vibrations. Infrared light is electromagnetic radiation with a wavelength longer than that of visible light, that is nearly less than equal to zero point 0.7 millimicron. 1 micrometer, where 1 micrometer is equivalent to 10 to the power minus 6 meter. Now, what is new in IR? In infrared spectroscopy, electromagnetic radiation of infrared region is passed through the molecules. The wavelength range of infrared region is 4,000 to 650 centimeter inverse, and its energy range is 1 to 35 kilocalorie per mole. By this amount of energy, transition of molecules from one vibrational energy level to another occurs. The transition is induced by the absorption of energy of infrared light of appropriate frequency which matches with the energy gap between the two levels. Now, vibrational motion. The vibration of the molecules means vibration of atoms of the molecules, and it is a to and fro motion, just like a simple harmonic motion. It has been observed that under ordinary condition, molecules are in state of constant vibration, with the individual bond having a characteristic stretching and bending frequencies and can absorb energy. The vibration of two atoms joined together by chemical bond may be illustrated with the help of spring and ball model. It is known that every spring has a vibrational frequency. Let us consider a ball connected to a spring which is held hanging by a hook and it stretched to a fixed distance and then released as shown in the picture. The ball starts moving to and fro with a certain frequency and amplitude. That is, a simple harmonic motion is generated. That is Hooke's law. Now, if another ball with a spring connected to it is attached to the first ball and the first ball is stretched to the same fixed distance, then released as before, it is observed that the this time amplitude and frequency become different from those previous one. This is the picture from this picture. uh, infrared we can say that infrared radiation is largely thermal energy. It induces stronger molecular vibration in covalent bonds, which can be viewed as a spring holding together two masses or atoms. Specific bond respond to specific frequency. And from the observation, it is evident that the vibrational motion in between two balls is dependent upon the following factors. Number one, strength of the spring, masses of balls attached to it. Third point, the system as a whole. Now, if spring is substituted by chemical bond and balls are replaced by atoms, we can conclude the molecular vibration is associated with the following factors. Number one, strength of the bond, masses of atoms attached to the bond, and the nature of the molecule as a whole. Now, what are the consequences due to IR radiation? Two types of change occur in a molecule. Number one, molecular rotations and molecular vibrations. Rotational transitions are little use of spectroscopy. And the molecular vibrations, the positions of atoms in molecule are not fixed. It can be regarded as a system of balls like atoms and springs like bonds. When such system absorbs radiation, it sets into a number of different vibrations. Consequently, deformation of bonds occurs. The deformation of bond may be due to two factors. Number one, stretching, and number two, bending. Now, what are the types of molecular vibrations? So, we are seeing that there are two types of fundamental molecular vibrations. Number one, stretching vibrations, and number two, bending vibration. To stretch a spring, more energy is required than to bend it. So bending vibration requires less energy and occur at shorter wavelengths than the stretching vibration. Now, what is stretching? Stretching is nothing but the change in interatomic distance along bond axis. There are two types of stretching vibrations, symmetric and asymmetric. Symmetric vibration. This is symmetric vibration. Symmetric. Symmetric stretching. Stretching. Stretching vibration. In this type of stretching, the movement of atoms with respect to particular atom in the molecule occur in the same direction. And in the case of asymmetric stretching, the asymmetric stretching, one atom moves in while other atom moves out. Now, coming to the point bending. What occurs in bending? Change in angle between two atoms. These are of four types: rocking, scissoring, wagging, and twisting. Among them, rocking and scissoring are in plane bending vibration, and wagging and twisting are out plane, out of plane bonding vibrations. In plane vibration means the bending vibrations in which the atom remains in the same plane, known as nodal plane of the system. These are two types: scissoring and rocking. What are the rocking? In this type of deformation, rocking deformation, movement of atoms takes place in the same direction. And in the scissoring, just like a scissor, two atoms approach each other. Okay. Now, this can be shown by this video. We can easily understand. We can get from this from the YouTube. Clearly indication of various type. This is symmetrical stretching. Movement of atoms with respect to the particular atom in the molecule occur in the same direction. And in the asymmetric stretching, one atom moves in while other atom moves out. One atom moves in while other atom moves out. Okay. One atom moves in, another atom moves out. This is scissoring, just like the scissor. Two atoms approach each other, swing towards opposite directions. Just like scissor. This is rocking. In this type of movement, the atoms takes place in the same direction. This is wagging, out of plane wagging deformation. In this kind, the bending of two atoms move up and below the plane with respect to the central atom. Two atoms move up and below the plane with respect to central atom. Wagging. This is twisting. In this type, one atom moves up the plane while other moves down the plane with respect to the central atom. And at a time, we can see all this matter, all these types of vibration at a time. We can also see from this link also. Symmetrical stretching, anti-symmetrical stretching, rocking, wagging, twisting, and scissoring. Now, this is the example carbon dioxide. Now, vibrational frequency. A molecular vibration occurs when atoms in a molecule are in periodic motion, while the molecule as a whole has constant translational and rotational motion. The frequency of the periodic motion is known as vibrational frequency. There are so many factors which affect the vibrational frequency, just like vibrational coupling, hydrogen bonding, electronic effect, field effect, and nature of solvent. And nature of the molecular vibrations in IR spectroscopy technique. Vibrational motion of a diatomic molecule is quantized. That is, the atoms of the molecule can vibrate at certain frequencies, and transition from one level to another can occur only when energy of the difference between two vibrational levels is absorbed by the molecules. And simple harmonic motion is the type of periodic motion, but the restoring force is directly proportional to the displacement. Here, this is the harmonic, simple harmonic motion. When it deviates, anharmonicity develops. And anharmonicity is the deviation of the system from being a harmonic oscillator. An oscillator that is not oscillating in harmonic, simple harmonic motion is called anharmonic. Here we are seeing that again I am showing. So this is V0 to V1. Actually, I should explain the details matter. The vibrational level 0, that is vibrational level 0 to vibrational level 1, that behave as harmony, and in absorption of radiation from IR region of the particular frequency vibrational transition occurs. The transition from ground state, this is V is equal to 0 means ground state, to the first state, excited state, absorbs light most strongly and give rise intense bands known as fundamental vibrations. But the transition from the ground state to the second or third excited state give rise the weak bonds known as overtones. It may be mentioned that since IR absorption bands due to fundamental vibrations are most intense, they are the most important for chemical study. However, in IR spectroscopy, most of the overtones are found in near infrared region beyond 4000 centimeter inverse. Such absorption are very weak. Now, vibration modes, normal modes of an oscillating system is a pattern of motion in which all parts of the system moves sinusoidally with the same frequency, and combination bands are observed when more than two or more fundamental vibrations are excited simultaneously. These combination modes arise from the anharmonicities of the oscillators, which leads to an interaction of vibrational states in polyatomic molecules. Overtones, that is multiple of given frequencies, result from excitation of ground state to higher energy states. Overtone occurs when we have already seen a vibrational mode of excited from ground state to vibrational level 2, which is called the first overtone, and where the transition occurs from ground state to vibrational level 3, the second overtones. Here, summarizations are there. First over fundamental, first overtone, second overtones, third overtones, and fourth overtone, where ground state to fifth level, vibrational level 5 occurs. Now, generally, molecular vibrations, which leads to a change in dipole moment of the molecule, will give rise to the absorption bands in IR. Otherwise, they are said to be IR inactive. For example, carbon-carbon double bond in ethylene has dipole moment 0 due to having center of symmetry. So its vibrational mode is IR inactive. Similarly, trans dichloroethylene is IR inactive, but its cis isomer is IR active. And next portion, next topics of this IR spectroscopy we will discuss in my next lecture. Thank you very much for our patient sharing. I am showing our online class during this lockdown period. Please keep patience.